Good evening, everyone. My name is Krishnateja Konduri, and I'm working in the Image Science and Computational Medical Physics Lab under Dr. Jin and Shui at UTA. Today, I'm going to talk to you about multi-phase computed tomography angiography and PCTA image denoising using RecycleGAN. As we all know, medical imaging is an integral part of the healthcare industry, mainly used for diagnosis. In this case, MPCTA is a widely used diagnosis tool for heart disease, which reveals artery blockage and heart movement. The radiation dose becomes a concern as a series of CTA images are collected during all 8 to 20 phases of the heart cycle. The common practice is to first collect high-dose images for several phases and low-dose images for the rest. Therefore, our goal in this study is to develop a spatial temporal deep learning method that could enhance the quality of low-dose CTA images. Previously, we have recently demonstrated that a state-of-the-art method, cycle-consistent generative adversarial networks, or CycleGAN, could effectively denoise low-dose CT images through spatial domain translation. As CycleGAN does not use temporal information in its denoising mechanism, we propose to use RecycleGAN, which could translate a series of images ordered in time from the low-dose domain to the high-dose domain. To validate RecycleGAN, we used the XCAP Phantom program, a highly realist simulation tool based on real patient data, to generate MPCTA images for 20 patients, 9 for training and 1 for testing. Our results so far show that RecycleGAN can achieve better denoising performance than RecycleGAN based on both visual inspection and quantitative metrics. So what are these limitations in CycleGAN that CycleGAN overcomes? CycleGAN, the translation is established only in the spatial domain. 2, CycleGAN fails to consider the temporal correlation along different cardiac phases. And 3, all of the first two reasons lead to suboptimal denoising. Therefore, the CTA images could be denoised better. How? RecycleGAN overcomes these limitations by 1, mapping the images using temporal constraints, 2, considering both spatial and temporal information while denoising the image, and finally, RecycleGAN has the ability to map between 2 image series through different domains. So now that I've given you a little bit of information on the background of our project and how RecycleGAN is better than CycleGAN, I'm going to talk to you how we set up our experiment to compare RecycleGAN and CycleGAN. Well, initially, we first extracted 18 patients worth of data from the XCAP Phantom program, 9 females and 9 males of the thorax, 8 phases of each cardiac cycle. We then split this data into 9 cross-validation sets to feed them into the deep learning methods. So first, we feed each cross-validation set into CycleGAN and RecycleGAN through various learning rates. And once we obtain the best learning rate for CycleGAN and RecycleGAN for each cross-validation set, we then feed the testing set using the same learning rate back into the deep learning method. And then we obtain the quantitative results for the testing set. This ensures a fair comparison between CycleGAN and RecycleGAN, and the cross-validation sets are the exact same for both CycleGAN and RecycleGAN to ensure a fair comparison. In the quantitative results table below, we can see that RecycleGAN is in fact better at denoising CTA low-dose images than CycleGAN. As you can see, the PSNR and SSI values for both female and male are much higher than CycleGAN. PSNR values measure how much of a signal there is than noise in the image. Therefore, higher the PSNR value, lower the noise. And the SSIM values measure how much of the generated image is closely related to the real image. Therefore, closer to 1 the SSIM value is, the better the images are, or the better the generated images are retaining their original artifacts. As you can see, even in the averages, RecycleGAN outperforms CycleGAN by a significant amount. Now we can go to the image comparison. The first row shows the generated XCAP Phantom images, and the third row shows the generated XCAP Phantom images as well, but different regions of interest through different cardiac phases. And the second row and the fourth row shows the images generated through the CycleGAN and the RecycleGAN deep learning method. As you can see, F3 is much more clear than F2, and F3 and F4 are images generated by RecycleGAN. And F7 compared to F6 are in fact much more better than F6. F7 has less noise and in fact also retains all its original artifacts compared to the real image. This in fact brings us to the conclusion of the poster. The performance of RecycleGAN is better than that of CycleGAN at all cases. Images produced by RecycleGAN are clearer and have less noise compared to that of CycleGAN. It shows the successful consideration of temporal and spatial constraints along different cardiac phases will indeed improve image quality significantly. In the future, We're planning to conduct a thorough evaluation on real patient data by repeating the same exact experiment, and we hope to see the same results. Thank you so much for listening, and have a good day.